Good afternoon, chemists. So let's get started. Just a couple announcements. I mentioned before that I'll be holding that Zoom midterm 3 Zoom session. It's going to be Monday instead, since I think we will finish the chapter fairly soon. All right. So yeah, we'll review on Monday, and that's via Zoom. So all that information is posted. I just posted the page with the links to the documents, to the Zoom stuff, all right? I will record it so you can watch it later in the week if you can't make it on Monday. Dr. W said that she is booking the room for her midterm 3 review in person. I don't know where it is. I don't even know what time it's at, but it will be on Sunday. So this Sunday. So just keep that in mind. So earmark that. I'll send you more information once I know more about it. All right. So on Monday, we dove off the deep end talking about valence bond theory and the details about forming molecules that, according to, Lewis structures, electrons are not just dots on a page. We have to consider their orientation, their shape. And so we use valence bond theory to help us achieve that. So we can actually correctly predict, based upon solving the Schrodinger equation, what molecules actually look like. So the big idea from this section in valence bond theory is that we have to hybridize central atoms depending on how many electron domains are around that central atom. Because we have to hybridize, because when we think about the pure atomic orbitals like S, P, D, those pure atomic orbitals, they are not in the correct orientation to get some of the unique shapes, the unique molecular shapes that we predicted earlier in the chapter, like tetrahedral. Like, there's no way we can get orbitals to overlap with just using P's and D's to make a tetrahedral shape. That's why we need to hybridize. So the big idea is that the number of electron domains around your central atom equals the number of atomic orbitals you have to hybridize. And that tells you how many hybrid orbitals you create. If you memorize one thing from this part of the chapter, it's that number of electron domains equals number of atomic orbitals to combine equals number of hybrid orbitals you get out. So we talked about 3 and 4 electron domains. 3 electron domains is SP2, where you combine 1 s orbital, 2 p orbitals. SP3 is 1 s orbital, 3 p orbitals. So now at this point, after 4 electron domains, we've used up all of our p orbitals. Because if you recall from chapter 6, when we have a p orbital, the L value, the L quantum number for a p orbital equals what? For a p orbital. L is number of angular nodes, 1. So what are the possible orientations, or the ML values for a p orbital? -1, 0, +1. So there's 3 different orientations for a p orbital. There are 3 different p orbitals. So once we're at sp3, we've used them all. So the next available atomic orbital to combine is not a p orbital. There's no such thing as an sp4. Instead, we combine a d orbital instead. So this is where we start to include our d orbitals. So going down here, so we talked about these 3, right? Like after 3 p orbitals, we're done. We don't have any more p orbitals we can combine. But if we have 5 electron domains, we're going to still combine s, p, p, p. There's 4. The 5th one is going to come from a d orbital. All right, that's the 5th atomic orbital that we combine here. So if we actually label these hybrid orbitals, you're just saying which atomic orbitals you combined. So for something with 2 electron domains, we say that it has sp hybridization. You're just telling the reader exactly what atomic orbitals you are combining. So the next one would be sp2, because there's 2 p orbitals. And the next one would be sp3. And then the next one, so that one has 4 atomic orbitals. The next one, 5. This is sp3d. And then the last one, 6 electron domains. We need to combine 6 atomic orbitals. The 6th one we add is an additional d orbital. So it's an s, a p, another p, another P, a D, and then another D orbital. So the hybridization with 6 electron domains is SP3D2, right? And this idea of expanded octets, right? So something with 5 and 6. So just to kind of tie it back to stuff that we learned earlier, 5 and 6 electron domains, those are things that have expanded octets. Do you recall the rule when we did Lewis structures? I said, when are expanded octets okay to do? Yes, when the central atom is in the 3rd period or lower. So ask yourself, what elements have access to d orbitals? What's the first d orbital? What's the n value of the first d orbital? Is it 1d? Is it 2d? No, it is 3d. So that's the reason why only elements that are heavier than n equals 3, so like usually we see it for like phosphorus and sulfur, those are why those atoms, those elements, anything heavier than that can have expanded octets, because they have access to low-lying d orbitals, because they are needed for hybridization. We see it all coming together? Okay, all right. So let's do some practice. I think this is, I talked a lot about valence bond theory, but the reasoning, because it's very conceptual, but I think the strategy for it is very straightforward, right? You start with the Lewis structure, you count the number of electron domains, you think about how many atomic orbitals or how many hybrid orbitals you need to make. So I think it's really systematic, as long as you have the Lewis structure. So yeah, my strategy here is first with these different compounds, a question would be like, what is the hybridization for that central atom, usually the first atom here. So I'm nice and I give you the Lewis structures. So in order to determine the hybridization of that central atom, you look at the central atom and you ask yourself, how many electron domains are around the central atom? So for that phosphorus, how many electron domains? 5. Because there are 5 bonds and there are no lone pairs. And so we just add up the number of bonds, the number of lone pairs, that tells you your electron domain number. So, you know, we can do the molecular geometry here based upon the electron domain number. What's the shape, the electron and molecular geometry for fun? Trigonal pyramidal, yes. So this is a very comprehensive question. Like we can answer a lot of different questions just about this PF5 molecule. So we can predict the shape from the electron domain number, but we can also predict the hybridization. So 5 is just the number of atomic orbitals that we need to combine. All right. So yeah, 5 electron domains, 5 molecular domains, because there's 0 lone pairs. So the hybridization of that phosphorus is SP3D. So we just need to combine 5 different atomic orbitals. Yeah. You tell me. So when we calculate whether something has an expanded octet, we count all of the lone pairs and all of the electrons that are being shared with it. So each of those bonds, those 5 bonds, counts as 2 electrons. So phosphorus has how many electrons around it? If we count both electrons in each bond? 10. So does phosphorus have an expanded octet? Yes, but according to the hybridization, does phosphorus have an expanded octet? It has a d orbital in it. So does phosphorus, from its hybridization, have an expanded octet? Yes, yes, because we need to add a d orbital to get that, go from 8 to 10 to expand it. Yeah? We see it? Okay. All right. Did we have our aha moment yet? No? What? No, it's period 3. Any period 3 and heavier. Yes, because, so remember how, so if you look and see where like the 3s and 3p are, yeah, it starts at like sodium all the way to argon. Those are your 3s and 3p. But remember, 3d is like one lower. See, remember how like when we fill up the electrons, it's a little bit out of order? All right, so phosphorus and anything heavier than that also can access those d orbitals. Okay, let's keep going. All right, bromine. Same idea. How many electron domains are on bromine? 5. In this case, it's 3 bonds and 2 lone pairs. No big deal, though. still 5 electron domains. So that means what is the hybridization of that central bromine atom? SP3D. So it's the exact same thing. All right, so another way to ask this question, so that's the hybridization of the bromine. I can also say, how many hybrid orbitals does bromine need to make here? 5. Yeah, remember, it's 5 electron domain, the number, equals number of atomic orbitals to combine, equals the number of hybrid orbitals you get out. So what that looks like, 5 hybrid orbitals on bromine. Remember, an orbital is a box. Are those 5 boxes? Yes? Okay. All right, so those are the 5 boxes. There are 5 sp3d orbitals on bromine. How many electrons does bromine have? 7. So let's fill them up, shall we? 1, 2, 3, 4, 5, 6, 7. Okay? So what do we see in that? We see 3 unpaired electrons to go make bonds with chlorine atoms. And then what else do we see? 2 lone pairs. Do you see that on that bromine atom? Dang. Ah. All right, let's do one more. All right, how many electron domains are on this bromine atom? 6. All right, so in this case, 5 bonds, 1 lone pair. But we can still predict the hybridization, right? 6 is our magic number. So this hybridization for that bromine is sp3d, 2 of them, yes. All right, so how many hybrid orbitals does that bromine need to make? 6. Do you want to draw the boxes? You want to draw the box? So how many boxes do I draw? 6. 1, 2, 3, 4, 5, 6. How many electrons does bromine have? 7. Place those 7 electrons. 1, 2, 3, 4, 5, 6, 7. So remember, these are 6 boxes, sp3d2. So what we see here are how many unpaired electrons? 5 unpaired electrons to go on and make 5 different fluorine bonds. And then there's our 1 lone pair. That's how it works, guys. All right, so that's valence bond theory. Okay, so let's wrap this up, all right? Let's wrap this up. So just really quickly, right, you should be able to look at any central atom and predict what the hybridization is, right? Because what's the thing, the criteria you're looking for? Electron domain. So going left to right, that first carbon is what hybridization? 4 is not a hybridization. It's just a number. So yes, there are 4 electron domains. We need to combine 4 atomic orbitals, but the hybridization is not 4. It is sp3. Okay, yes. So 4 is the magic number, but hybridization is sp3. Okay, next one. The next carbon atom. sp3-2, because that double bond just counts as 1 electron domain. We'll go into more details about that later. Okay, what about that last oxygen? sp3, because there's 1, 2, 3, 4 electron domains. Okay, so the next slide, I can ask the question a little bit differently. It seems like a harder question, but I promise it's not. So here, I'm not pointing to the atoms, right? I don't just say, like, what's the hybridization of that carbon? I say, what are the orbitals involved in the formation of this bond? But really what that question is asking is what 2 orbitals are involved in that bond. So you just look at the 2 adjacent atoms and you ask yourself, what are the hybridizations of those 2 adjacent atoms that combine to form that bond? So if we look at the first bond, what 2 atoms are involved in this first bond right here? There's a hydrogen and a carbon. So you need to ask yourself, what orbitals are overlapping to create this bond? So first we'll look at hydrogen. And really what it is you're thinking, where's that unpaired electron? If this was, a Lewis structure, we would, combine those 2 unpaired electrons to make a bond. But now we're thinking, what orbitals are those dots, those electrons in? So for hydrogen, does hydrogen undergo hybridization? No. When hydrogen is involved in a bond, it's always its 1s orbital. That's the unpaired electron. So then we name where is that unpaired electron in this carbon atom. And basically you just say what the hybridization is. We already determined the hybridization of that carbon. What is it? SP3. So the orbitals involved in making this bond is a hydrogen's 1s orbital and that carbon's SP3 orbital. Those are the two orbitals overlapping, making that bond. So the next bond, again, you just look and think, okay, what are the hybridizations, the orbitals involved in the two adjacent atoms? So kind of just going left to right, we again are working with this carbon again, so that carbon's SP3 orbital is overlapping with the second carbon's SP2 orbital, yes, okay. All right, the next one, so we start with that SP2 carbon again, and it's overlapping with this oxygen, which is what hybridization? SP3, very good. And then this last one, it's the oxygen's SP3 orbital overlapping with a hydrogen's 1s orbital, very good. All right, so that's just another way to ask the question, but it really is kind of the same thing as the previous one. All right, there we go. All right, so so we'll go into a little bit deeper into valence bond theory and talk about multiple bonding, because we said within Lewis structures and Vesper theory, they didn't distinguish single, triple, double bonds at all. The strengths of valence bond theory is that we can talk about double, triple bonds and what makes them unique based upon the idea of orbital overlap. So let's do this again. What are the hybridizations of these two carbons? Yes, SP2 and SP2, all right? What about the hybridizations of these two carbons? SP1, or just SP, yeah, SP1, because there's two electron domains and another SP1 within there. So the idea here is, okay, with these carbon atoms, we didn't combine all 4 atomic orbitals, that we have some leftover p orbitals, right? Because there's 3 different p orbitals, they're different orientations. For the first one here, we only combine 2 of the p orbitals. So there's this leftover piece that might do something special coming up. Or in the second picture, when we build those hybridized carbons, there's 2 leftover p orbitals, and they might go on and do something special. And that's the whole idea of multiple bonding, and we use valence bond theory to describe it. And so it's the idea of what are those leftover p orbitals doing? All right, so yeah, multiple bonds. So this is kind of related to valence bond theory. We need to think how orbitals are overlapping with one another. Okay, so been lying to you a little bit so far about the idea of, single, double, triple bonds. I always tell you that, as bond order increases, strength increases. The thing is when we say it increases, most people think like a linear trend, right? That like a double bond is twice as strong as a single bond, right? Like a normal person would think that. Or a triple bond is 3 times as strong as a single bond. The thing is that it's not. And the reasoning is because of how the orbitals are overlapping using valence bond theory. So just to get some definitions out of the way, all right, so just this is something you need to memorize. A single bond is 1 sigma interaction, right? So this is a sigma right there, so sigma. And so what that means, a sigma interaction is when, now we need to think of, okay, I told you that a bond is formed when orbitals overlap, but we need to think about how can orbitals overlap? What is the orientation of them? Do the orbitals overlap this way? All right, with like a head-on type of overlap, or do they overlap kind of side by side? And so those ideas give us different degrees of overlap, different strengths, and so we have different interactions here. So a sigma bond All single bonds are sigma bonds. And we have pi interaction. So a pi interaction is the second component of a double bond. So here you see a double bond is a sigma component plus a pi component. So a pi component has this is the side-by-side interaction I was talking about. So a double bond, it's not two sigma interactions. It's a sigma plus a pi. And then a triple bond is a sigma interaction plus a pi interaction plus another pi interaction, all right? So we have two different side-by-side interactions going on. So this is just something you need to memorize. And just for fun, just let's guess what a quadruple bond is. Quadruple bond means bond order of 4, okay? So what's the first component of a quadruple bond? Just try to find some trends here. Sigma, yes, okay, very good. Sigma. What's the second component? A pi. The third one is probably another pi. And then the fourth one, I knew you were going to say pi, but it's not a pi. It's not a pi. It's actually a delta. It's a delta. And I'll actually show you why a little bit later, okay? All right, so let's just go. That won't be on the exam, all right? All right, so this is the example I'm going to show, kind of going step by step how a pi bond, how a double bond is made. All right, so lots of ideas here. Hybridization, the idea of hybridization, Vesper theory, all those things. Okay, we're combining all of those things together. So we're looking at both of the carbon atoms, both of those carbon centers. So if we look at each carbon center, what's the hybridization of each of those carbons? SP2. Yes, they're trigonal planar. That's what Vesper theory says. Valence bond theory says that it's SP2 hybridized. So let's keep track of every single electron and what is overlapping with what. Okay, so we said that each carbon, so we need to do this twice, right, is SP2 hybridized. So there are 3 electron domains. So we hybridize how many atomic orbitals? 3, and that's what we see here, right? We see 3 atomic orbitals that we hybridize. So when we hybridize them, right, we have a new SP2 hybrid set. See how we have 3 boxes? 3 boxes for 3 electron domains. But then carbon has how many valence electrons? 4. So we need to place those 4 electrons. So we place them all singly, right? 1, 2, 3. The fourth one, because this unhybridized p orbital, it's actually a very similar energy as these hybrids. That fourth electron goes into that unhybridized p orbital. So note here how on the left side I have 4 atomic orbitals, but I hybridize 3 of them. This leftover one doesn't go away. This leftover orbital, that leftover box, it doesn't go away. It's still there on this side. It's just on the end. All right, and note here I was very specific about the orientation here. So the only orbital, the p orbital I didn't include is just if we're thinking about the XYZ axis, it's the p orbital on the z axis itself. All right, so we have our 4 electrons all spread out within there. So what we see here is that these hybrid orbitals make that trigonal planar shape that we know and love from Vesper theory, all right? So let's recall, remember this picture is wrong, right? These are 3 different orbitals. Each of them have how many electrons in each of those lobes? 1. There's 1 electron in each of those lobes because each of these boxes is a lobe, all right? So let's look at the details of how we form this molecule. Okay, so recall, so we hybridized our carbon. It's SP2, right? And so remember, we have 2 carbon atoms. So I have this whole SP2 dealio twice because we have 2 carbon atoms. And that's what you see here. Carbon with 3 different SP2 hybrid orbitals. This carbon with 3 SP2 hybridized orbitals. So we see where we're combining electrons to form bonds. Okay, so I've drawn where all of those unpaired electrons are. So recall, this picture is basically the same as this picture. In this first picture with the boxes, I don't show the orientation, the shape of the actual orbital, the hybrid orbitals themselves, but in this picture I do show them. And so now we're just thinking, okay, in 3-dimensional space, what electrons are pairing up? So we see that the hybrid orbitals, one of the bonds that are made, those electrons that are shared, are between the carbon and carbon atoms themselves. And so this interaction between two hybrid orbitals, is this a sigma interaction or a pi interaction? Sigma, because the two orbitals are like going head on at one another. All right. So let's look at the other electrons. So let's inspect this bond. We have a hydrogen's 1s orbital, because there's hydrogens in ethene, and then another sp2 hybrid orbital overlapping to create the carbon-hydrogen bond. So we have like a sphere for hydrogen and an sp2 orbital coming in this way. What type of interaction is this? Is this sigma or pi? Sigma. It's another sigma. It just so happens to be with an s orbital, and that's okay. It's still this type, yes, this type of interaction. All right, and we basically see the same thing for all of them. So this is a sigma interaction, carbon-carbon. This is a sigma interaction. This is a sigma interaction. That's a sigma interaction. That's a sigma interaction. So what we've learned here, okay, is that all hybridized orbitals, if something's hybridized, those orbitals will always make sigma bonds. They'll always make sigma bonds. So the idea of, okay, we have all of the sigma bonds accounted for, but if we count the number of electrons here, in that picture, there's only 10 electrons pictured there. But if we, do the Lewis structure deal where we count all the valence electrons, we need to actually place 12 valence electrons total for 2 carbons, 4 hydrogens. So the idea is we have 2 electrons unaccounted for. Where are the unaccounted electrons? Where are they? They're in those unhybridized p orbitals. We have not taken into account these 2 electrons yet. And this is the idea of where the pi component of a double bond comes from. All right, so that's what we did. So we have those 2 unaccounted electrons. They're coming from the pi component. The pi component, a pi bond is formed from 2 adjacent p orbitals. All right, so these p orbitals on the carbon atoms, they are in and out of the plane of the actual molecule. So the molecule, if you look back at the other picture, the previous picture, this whole carbon hydrogen framework with all of the sigma bonds, they're all in a plane, they're all flat. Okay, so the p orbitals, the unhybridized p orbitals, are actually coming out of the page. They're coming out of the page and down into the page. So those are where the p orbitals are, and that's what this picture is trying to show you. Like, hey, these are all the sigma bonds that make the sigma framework. There's 2 electrons in each of those lines. But the p orbitals, the unhybridized p orbitals, are in and out, or like up and down, perpendicular, that's the word, right, to the plane of the molecule. And so this interaction between unhybridized p orbitals, it's like this. It's not like this. So this is a sigma bond when it's head on, versus side-by-side interactions. This is a pi interaction, and it's weaker. Like, you think, like, that's not really looks like an interaction, and you're right. Pi interactions are weaker than sigma interactions. This is like very clearly there's overlap happening when we bring 2 orbitals head on like this, but when they're side by side, there's some overlap. Pi interactions are weaker than sigma interactions, but it's still stabilizing nonetheless. All right, so that is our pi interaction. And so a question before was, I think we were looking at a double bond like this, ethane, and the question is, does that bond rotate? Does that bond rotate? And the reason, and I said no, so ethene does not rotate. That molecule does not rotate because there's a double bond present. That double bond, because of this side-by-side overlap, if we rotated those carbon atoms, we'd rotate those PZ unhybridized orbitals, right? So if I rotated one of the carbons and I went like this, I would actually have to break the double bond. And so that's why ethene and these double bond molecules, they do not rotate in space, because you would actually have to break the pi component. So I think the question was like, does it rotate, does it twist? No, it doesn't, when there's a double bond present. Okay, so a little bit more detail about these sigma interactions. It's a bond. When I say sigma, when I say pi, I'm talking about bonds between 2 adjacent atoms. The Greek letter indicates what type of overlap it is. And so I just like to remember sigma interactions are head-on overlap. So there's a bunch of ways we can accomplish that. We can do head-on overlap between two s orbitals, like in diatomic hydrogen. So again, we're thinking about where are those unpaired electrons, okay? And we're thinking about how are those orbitals overlapping in space? Are they head-on or are they side by side? So for sigma bonds, you see we can have s orbitals combine in that head-on overlap. We can also have an s and a p orbital. You can see how in all of these examples, the overlap is the same. The part where the electrons are sharing the space, see how they're all the same? All right, and so that idea of how it's actually overlapping gives us the idea of a sigma interaction. Okay, and these interactions are fairly strong. They give us the best overlap, so they give us the strongest type of bonds here. And so more examples, what sigma bonds do is they concentrate electron density between the atoms themselves, the two atoms that are involved in the bond. And no, all single bonds are sigma bonds. And all of our rest of our, like, double, triple, quadruple bonds, the first component is always sigma. All right, so pi bonds. We said if there's anything you memorize, okay, it's that pi bonds can only be made by unhybridized p orbitals and sometimes d orbitals. But you never can make a pi interaction with a hybridized orbital, ever, ever. Write that down. So the first thing is that side-by-side overlap of unhybridized p orbitals. That's how we make pi interactions. So that means that hybridized orbitals, okay, like your SPs, your SP2s, whatever, those orbitals cannot make pi bonds, ever. Hybridized orbitals can never make pi bonds. It's only the leftover unhybridized p orbitals that can. All right? Did you write that down? Yeah? Okay. All right. So those are our pi bonds made by p orbitals. They both start with p, right? Yeah. Yeah. P pi. But never, you can't use hybridized orbitals to make pi interactions. And the reasoning is because of the orientations, okay? That pi bonds, they're side-by-side overlap. And so the whole deal of hybridizing atoms is to get them into the correct orientation of your sigma network, or to get to your electron geometry for that specific molecule. And so the orientation of the overlap won't be correct there. And so what we see here, this is ethene again. So the yellow lobes you see, those are your sigma bonds, all right, that you're making with different hydrogens and the carbons themselves. So see how that's head-on overlap, like here, and there. Those are all sigma bonds. And so our pi interaction is what's going on above and below the internuclear axis. And this is why double bonds can't twist. That's why they can't twist, yeah. Don't worry about the phases. It's the whole idea that electrons are both a particle and a wave, and wave functions, we can add them constructively and destructively, but that's out of the scope of this class. Okay, so yeah, they have different phases. So really, it's whether we're in the positive or negative side of the solution to the Schrodinger equation. But don't worry about it. Okay, all right. And this basically just summarizes what I just said. Single bonds are sigma interactions. A double bond will always have a sigma interaction, which is usually between the hybridized orbitals themselves, and then one pi interaction. The pi interaction is made between two what kind of orbitals? Two unhybridized p orbitals, always. Okay? And so a triple bond consists of a sigma interaction and two pi interactions. All right? So a triple bond, think about this critically, how many unhybridized p orbitals are involved in a triple bond? How many? So a triple bond has how many pi interactions? Two. Okay. How many unhybridized p orbitals do you need to make a pi interaction? 2. So there has to be 4. Half of you got it. Very good. You need 4 unhybridized p orbitals to make a triple bond. Okay, all right. And this whole idea that the pi component is weaker than this, the single bond. So here, if we just look at like carbon-carbon, single, double, triple, like you would think that it would be, when we would go to a single to a double, it would be twice, right? It would just be double the number, but it's not. We see when we add the pi component, it's a little bit less than double, okay? It's stronger, yes, but not double stronger, all right? And then the second pi component that we add is, again, less than 346 kilojoules per mole. And so, again, that kind of indicates the whole idea that a pi interaction is overall weaker. There's less overlap than a sigma interaction. All right, so let's show another example of hybridization. And here's the thing I told you to write down, right? Hybridized orbitals will make your sigma bonds. Unhybridized p orbitals make your pi bonds. Okay, so let's look at this molecule, formaldehyde. So I want you to concentrate on that double bond right there. Okay, so we got carbon and oxygen. What are the hybridizations of those two atoms? So carbon is SP2 and oxygen is SP2. So if we write the boxes for that, how many hybridized orbitals are on that carbon atom? 3, yes, because there's 3 electron domains, meaning that there's 1 unhybridized p orbital left over. This is carbon, okay? Let's do the same thing for oxygen. How many hybrid orbitals are on oxygen? 3, because it's sp2, there's 3 electron domains, okay, so 3. Then that means there's 1 leftover unhybridized p orbital, okay? So that's oxygen. Let's fill up our electrons. So for carbon, there's 4 electrons. 1, 2, 3, 4. For oxygen, how many electrons are there? 6. 1, 2, 3, 4, 5, 6. Okay, what's going on here? So if we look at this picture, I'm going to move stuff around. So there's my oxygen. There's my carbon, all right? Carbon, oxygen. Okay, so these purple boxes is basically our sigma network, all right? So there's a sigma interaction between the carbon and the oxygen. There's a sigma interaction because a double bond always has 2 components, sigma and pi. Okay, so that type of overlap right here, that's my, this right here, that's my sigma interaction. That's between one of these sp2 hybrids on carbon and one of the sp2 hybrids on oxygen. These 2 electrons are overlapping to make my sigma bond. So note here how there's only 1 unpaired electron on oxygen, right? That oxygen only makes 1 sigma bond. Even according to the picture, like if you look at formaldehyde, like it looks like that. That oxygen, because there's 2 lone pairs on it, there's only 1 sigma bond attached to it. You see that? And so that's what we see here. There's 1 sigma bond there. What else is on oxygen? On these sp2 hybrids, what else is there? 2 lone pairs. Do we see that in the Lewis structure? Yeah, we do. Isn't that beautiful? Okay, so yeah, these are our 2 lone pairs. And then our carbons, okay, we have 2 other unpaired electrons. What are those doing? Making bonds to hydrogen. Yes, that's what you see right here. Both of those are making bonds to hydrogen. Okay, so we talked about the sigma, the hybridized network. Those are where all our sigma bonds are. What we haven't talked about is the pi, the unhybridized p orbital. So these 2 electrons, those electrons are hanging out up, like in and out of the plane of the molecule. And that is what's creating the double bond in the molecule itself. So really what that is, it's these pink boxes right here, okay? There's a total of 2 electrons in that whole interaction, and it's side by side, so that's why we call it pi. And because there are electrons that are in a sigma orientation between the carbon and oxygen and in a pi interaction between carbon and oxygen, that's why there's a double bond between those 2 atoms. So we went into like an obscene amount of detail about bonding. This is an advanced theory of bonding. Like it's very, very advanced. So I hope you feel very smart. Hope you feel very smart. Okay, do we see it all come together? We see it all come together? And it all builds, like you need the Lewis structure, you need to predict molecular shape and get it right. So you can predict hybridization and then inspect valence bond theory to look at multiple bonding scenarios. Yeah. It is on the top and bottom, yes. So it's above. So if you look at the previous slide, it says that pi bonds are, the electron density is both above and below the inner nuclear axis, so both at the same time. And I'll say that within the chemistry education community, sometimes you see these with phasing. So like here it's red and blue. Sometimes you see it without phasing. Don't worry about the phasing, all right? So just know that pi interactions, you have electron density above and below. So yes, so both of these this picture and this picture are both correct, even though the colors are not. Okay, so let's look at one more, all right? So ethine or acetylene, so it's a carbon-carbon triple bond. So a triple bond has what components to it? A sigma, a pi, and another pi. And we already said that a triple bond needs 4 unhybridized orbitals to make that happen. And that's actually exactly what we see here. So we have 2 different carbons that are sp hybridized. So if they're sp hybridized, these hybrid orbitals, that's involved in our sigma network. But then we have 2 leftover unhybridized p orbitals. And so we have this twice, right? Because we have 2 carbon atoms. So basically, yeah, we have it twice. Do I have it down here? No, I don't. So we have it twice. So we have like another set of hybrids and another set of unhybridized p orbitals. So these electrons are involved in our pi interactions, and these ones are involved in our like carbon-carbon and carbon-hydrogen bonds that we see. So what's kind of interesting here, this is why we have, it's linear. So this bond makes our carbon-hydrogen bond. We have a carbon-carbon here, carbon-hydrogen here. But what's kind of fun is we see 2 different pi interactions, but they're in different planes. So in the previous example, we saw the pi interaction on the z-axis. All right, so I think it was like right here. So that's on the z-axis. We have another pi interaction that's perpendicular to it going this way. All right, I don't know what axis that is. Let's call this the x-axis. So then the red here would be the y-axis. So there's 2 different orientations. Because this molecule is linear, right, there's no plane to the molecule. It's just like a straight line molecule. We have a pi interaction going this way and this way. So that's pretty cool, right? Okay, there we go. I think that's it. That's it. So this is what it looks like, all right? That we have 2 different pi interactions. It's kind of, yeah, you see it right here. One's right there. Let's say it's on the x-axis, and then another one right there, that's on your z-axis, all right? And so there's a lot of different interactions going on here. But really, the big takeaway is that hybrid orbitals, those are the ones that are involved in your sigma network. It's unhybridized p orbitals are always the ones that are involved in pi bonds. And the reasoning is because pi bonds are this type of interaction, and really only p orbitals can achieve that. Like you can't do that with s orbitals. All right. Okay, so I think, oh crap, just a little bit more. All right, so the idea of pi interactions is going to complete the picture of the idea of resonance that we talked about in the previous chapter. So when we talked about resonance, it was always within molecules that made double bonds, right? Where you would draw the Lewis structure, and there'd be many different ways you could complete the Lewis structure or complete the octets by making double bonds. That's why, that's how we identified a molecule that has resonance, when you could finish the multiple bonds in multiple different ways. And so let's take the idea of pi bonds to that picture. So if we look at benzene, benzene has alternating double and single bonds, right? Right? So like right here, that's a double bond. There's a sigma interaction and a pi interaction. But if we look at each of these carbons separately, right, each of those carbons are what hybridization? They're all identical. SP2. SP2. The SP2 hybrid orbitals, those are making the sigma network. Each carbon has how many unhybridized p orbitals? 1 because they're SP2 hybridized. So that's the picture that you see here. Here's the sigma network. Those are all the hybrid orbitals that make the sigma interactions. We just said that there is one unhybridized orbital, unhybridized p orbital on each of those carbon atoms. So the idea is, okay, 2 electrons have to overlap to make a bond. But if you're an electron in that the unhybridized p network, if you're an electron there, do you want to make a bond with the carbon on your left or on your right? It's the same, right? Like it would be the same. So this is the idea of hybridization, that they're really, it's not that one electron is sharing solely with the other electron next to it on its left. It could equally share its electron density with the electron on its right. And so it's kind of more like socialism. They all share together, okay? So yeah, instead of just, being, a 2-person bond, they all bond together. Do you see that? Right, like you could do these 2 in a bond, or that electron could do these 2, but really in actuality, they all share together. And that's the idea of hybridization, that we could draw it this way, the pi bonds this way, but it doesn't exist that way. Instead, we just smear that electron density, all the pi clouds together. And that's why we draw benzene the way we do often, which is reflective of its delocalized double bonds. We draw it like that, and really it's reminiscent of its pi cloud. And so Kekule, when he was high on opium looking at that wheel, was thinking that. Obviously, he was thinking about delocalized pi electrons, right? Yeah, so there we go. Okay, so that kind of, that summarizes it, all right? So valence bond theory, there was a lot there, okay? We talked about valence bond theory. Orbitals have to overlap to make chemical bonds, and they have to be in the right orientation for it to agree with Vesper theory, to get us the weird shapes that we saw, like sea salt, tetrahedral. We can't do that with pure atomic orbitals. So now this new part of chapter 9, it's the last part, and it's the most advanced theory of chemical bonding, covalent bonding, and it's MO theory, all right? So molecular orbital theory. So we've been talking about atomic orbitals. They're made from atoms. Hybrid orbitals, also made from atoms, but we mix atomic orbitals. Molecular orbitals come from molecules, yes. So we're bringing atoms together now, okay? And so MO theory is super powerful. It helps us explain a lot of different things, okay? But it's very tedious, okay? So if we can use a simpler theory to answer a question, typically we will. But MO theory is really, really powerful because it helps us do a couple things. So just to showcase, these are what typical exam questions will be like. It'll say something like this, okay, which molecule here is predicted to be diamagnetic? Diamagnetic means does not respond to a magnetic field, meaning that all of their electrons are paired. So here you are given these 2 diagrams. You'll always be given them. They are on that supplemental handout that I already have posted for midterm 3. You just need to know how to use them, okay? And so I will explain what these diagrams mean. It looks harder than it really is, okay? We can't answer this yet. I just wanted to show an example. Okay, what is MO theory? It is us finally recognizing that electrons are not only particles, but they are also waves that have wave functions. So as you can do with waves, when you add them together, they can add constructively or destructively. That's the whole idea. So if we have 2 atoms, each with their own wave functions, atomic wave functions, when we bring them close together, we add their atomic wave functions, but get a new wave function. But it's no longer called an atomic wave function or orbital. It's now called a molecular orbital because we brought 2 atoms together to make a molecule. So that's basically the whole idea. So when we combine 2 orbitals on atoms, we get We describe bonding between atoms, and that is called a molecular orbital because we're making a molecule between two atoms. Molecular orbitals can have different properties, and it's based upon the phasing and the mathematics behind this process. We can either have bonding orbitals, which strengthen bonds. We can have anti-bonding orbitals, which are typically denoted by a star or an asterisk after it. And we can have non-bonding orbitals, but we don't talk about those. We're just going to talk about these ones, bonding and anti-bonding. So the great thing about MO theory is that it's going to allow us to do kind of the last things that I said that Vesper theory couldn't do, and that's predict bond order, and whether molecules exist or not. It can also predict paramagnetism or diamagnetism, so whether a molecule will respond to a magnetic field. So I'll just note that paramagnetism means that we have unpaired electrons, at least one. Okay, so at least one. Something that is diamagnetic means everything's paired. Yeah. No, so it's, so when we, in chapter 6, talked about the radial distribution function, right? And we did things like this, right? For like this is like a 2s orbital, okay? And when we saw, I don't know if you looked at the y-axis, probably not, but I wrote psi squared, so it's the wave function squared. So this is the probability of finding an electron. It's the value squared. But if we just plotted psi instead, it would actually look something like that instead. And so that is what phasing is. But we ignore it because we work with psi squared. What? Yeah, that's why we square a lot of things in life. Yeah, so there's no negative values because people don't like negative signs. Yeah. Okay, is that sufficient? You're not going to be assessed on it. Okay. But you get me going. So I have to, okay, all right. So waves, they can add constructively, destructively. The whole idea of MO theory, we're bringing atoms together to make molecular orbitals, okay? So the atomic orbitals combine to make molecular orbitals. So here's a trick question for you, or not really, okay. So when we hybridize things, right? If I combine two atomic orbitals and I got two hybrid orbitals out, right? So in this picture, I'm combining two atomic orbitals on hydrogen. How many molecular orbitals do you think we'll get out? Okay, so when I combine two atomic orbitals to hybridize, I got two hybrid orbitals out. 2, 2. So if I combine two atomic orbitals in MO theory, how many molecular orbitals do I get out? 2. 2. Okay? If I combine 5 atomic orbitals, how many MOs do I get out? 5. Very good. Okay. So I will show you those MOs that we get. So waves can add constructively or destructively. So in this picture, what we see when the phasing is correct, so yes, the plus or minus part, but it doesn't matter. Just when they add constructively, these two things, we get an orbital that is more stable, a molecular orbital that is more stable than the two atoms alone. All right, so this is, we call a bonding orbital. When we think about two s orbitals coming together, what type of interaction is that? Sigma. So we call this orbital a sigma 1s. We want to say that this is an MO, right? It's a molecular orbital, we're combining atoms, but we also want to say what type of interaction it is. It's sigma, and also between what atomic orbitals do they come from. So we say it's sigma 1s, right? This is constructive interference here, and the phasing is correct. So on the other hand, if we have constructive, right, that means we can also have destructive addition between atomic orbitals. So this is that second molecular orbital. I said if we combine two atomic orbitals, we get two MOs out. So we talked about the first one, that's the bonding MO. This is the anti-bonding MO. So it's this top one, where the phasing is opposite. See how it's the phasing's opposite here? See that? but in here it's the same. Okay, so there we go. So this, the bottom one we already did was our sigma 1s, and then the top one up here we also call sigma 1s, but because it's anti-bonding, we give it a star. All right, and so what this orbital actually looks like is there's not as much electron density between the atoms themselves. Anti-bonds make atoms, or bonds weaker, while putting electrons in bonding orbitals, like in our picture before, strengthen bonds. So let's just, to finish up here, what we see, okay, this diagram, this is the basis of MO theory. What we see over here on the sides, these are our atoms, okay? But in between, we see the hydrogen-hydrogen molecules, so bringing them together. So we have atomic orbitals on the sides, and we have MOs in the middle. So we have to, I think the next step here is we need to fill these orbitals following Aufbau's, Pauli's, and Hund's rule, just like we've done before. So the answer is right there, but I want us to arrive at it together. So we have a total of how many electrons in hydrogen, diatomic hydrogen, how many electrons do we have to place? 2, because there's 2 hydrogen atoms, 1 electron each. So we fill the MOs with the appropriate number of electrons. So where are the electrons going to go? In the bottom. Right? Where's the next electron going to go? Still bottom, but do I put it like that? No, right? That gives you anxiety, right? No, you need it to spin the other way. So when we fill up MOs, it's just like we did before. With atomic orbitals, we need to follow all of those rules. You fill from the bottom going up, you follow Hund's rule and Pauli's exclusion principle. Okay. What? Good? Thanks. You never, does that mean all the other classes I didn't do well?